Hi everyone, this is Mrs. G, and today we're going to do a general integration overview. Alright, I have a quick warm-up for you guys, so please pause the video and give each of these a try. Alright, go ahead and check your work here. So some of these hopefully you just recognize right off the bat, like for arctangent, arcsine, and arcsecant. So hopefully you remember those integration or your derivative rules backwards. But like for number B, we do need to use U-sub to help us with this one. Note here, well, the antiderivative is that natural log of the absolute value of U. When we substitute back in, 1 plus x squared is always positive, so we don't need the absolute value signs. And then for part E and F, we also need to use U-sub. And then for part F, after you use your U-sub, hopefully you recognize this again for arctangent, and then you could substitute back in. So here's a list of many of the derivative rules that we learned from first semester. Hopefully you remember all of these. As we've been working with integrals, of course, most of them are just, or many of them are just our derivative rules, but working your way backwards. But, you know, a lot of people kind of forget about, especially the inverse trig functions. So make sure you still have these committed to your memory as well as your all of the other ones we covered. And then here's just a table of our some of our integration formulas. So again, some of them are pretty straightforward, or it's more just your derivative rules but working backwards, but some of them are not as obvious, but would definitely be worth memorizing, like if you have like 11 through 14, so the integral of some of our different trig functions. So again, these would be really nice to know. Some of these we did do. You can find these antiderivatives using U-sub, but it's might be useful just to memorize some of them. And then as well as recognizing some of these for our inverse trig functions. So kind of going off of all of those integration formulas that we just looked at, sometimes our integral is not a perfect fit for those, but we can turn it into one of those patterns or rules. So these are just different techniques that allow us to do that. So we'll take a look at a lot of these today. One technique could be expanding, so like multiplying out a binomial. Another technique could be separating a numerator, so taking a single fraction and writing it as 2 or more. Another one, which we will do today, is actually completing the square, typically within our denominator, to fit one of our inverse trig functions, our derivative rules for that. So again, kind of manipulating the original formula to fit a pattern where then we can use U-sub to help us. Another common strategy, if you have a fraction like this, is to do long division to rewrite it as a mixed number or a mixed fraction. This next technique is not as intuitive, but sometimes it could be beneficial to actually add and subtract the same term in our numerator. So here you can see we just added 2 and subtracted 2, so we didn't change the overall value, but in doing so it does allow you to rewrite your equation, to split it up into 2 parts and potentially recognize a pattern for one of those. So maybe one of those fits one of our formulas better than our original form. We will also be working a lot with our trigonometric identities, so definitely make sure you know your Pythagorean identities. It might be useful to know our double angle formula or our half angle or power reducing formulas, so those will be really useful for us. And then sometimes we will also multiply and divide by a Pythagorean conjugate to help us, you know, rewrite our original integrand in a different way. So a big part of today's lesson is going to be just really learning to recognize pattern and structure within your integrand. So noticing if something fits one of our formulas that we've talked about. So if you look at this, we do have a constant on top, which we can always kind of, remember, we can always move it out front. So when I look at this, I definitely see this structure, which would be the derivative of arctangent. So hopefully right off the bat, you notice that we can just evaluate this integral as 4 times the arctangent of x, and then we have our constant of integration because it's just an indefinite integral. But then if you look at this next one, it looks really similar, but here I have an x in the numerator. So it actually does not fit this structure, and we can't take a variable and pull it out front. So for one like this, we would have to try something else. We could try u sub. So I'm going to set u equal to x squared plus 1, 2x dx, and then I can do a couple things here. So I'm going to substitute for x dx, and then I'm also going to move this 4 out front. So when I do that, I have the 4 out front and then times the 1/2. So it just gives us 2, and then everything else will substitute out. So 1 over u du. And then from here we can evaluate. So we know it's the natural log of the absolute value of u. And then we can substitute back in. And again here, we know that x squared plus 1 is always positive. So 2 times the natural log of x squared plus 1 plus c. So again, this is really just recognizing the difference between these two. They look super similar. Here, it's one of our structures. Here, it is not. All right, let's try another one together. So I know this one looks different than our last example, but to me, I do kind of see this type of structure, which again would be the derivative of arctangent. So I'm going to see if I can kind of rework this a little bit to kind of fit this pattern more. So first of all, I notice, well, I have this 4 out front. I have a 4 here. We would like it to be a 1. Maybe I can factor out a 4 altogether and see what that looks like. So I'm going to factor out a 4 just from my denominator, and then I have 1 plus 9 over 4 x squared dx, which then I see that I can just simplify this out altogether. So I have 1 over 1 plus 9 over 4 x squared dx. So it looks like I'm a little bit closer, but I know that I'm going to need to use some type of u sub, and I need to fit this a little bit better. So then I'm wondering if I can rewrite this to help me out with that. So I'll say 3 over 2x and then all of that squared. So then when I do my u sub, I end up with 1 over 1 plus u squared. So I can set u equal to 3 over 2x. So then du is just 3 over 2 dx, which of course we can just pull this out front when we substitute. And then that allows me to rewrite it in a form that I like. So I have 2/3 times the integral of 1 over 1 plus u squared du. And so in doing this, I've now created that structure that allows us to evaluate, and it would just be arctangent of u. So we have 2/3 times the arctangent of u plus c, and then we're just going to substitute back in for u. So 2/3 arctangent of 3 over 2x plus c. So again, this one's definitely a little bit trickier, and we need to do a little extra legwork, but hopefully just recognizing that this looks kind of like this structure, then we can kind of go out of our way to rewrite it to make it a little bit easier for us to evaluate. All right, so go ahead and pause the video and give this one a try on your own. All right, go ahead and take a look here. So for this one, again, I can kind of see that there's some type of structure that could look like arctangent. If I rewrite my denominator as 1 plus e to the 2x squared, it allows me to use u sub. So I can set u equal to e to the 2x, and then I can substitute out e to the 2x from my numerator, and then when I do that, I have the derivative of arctangent. So it allows me to integrate pretty easily. All right, let's try another one together. So here I have the integral of the cotangent of x times the natural log of the sine of x dx. So this is kind of an interesting example. I'm going to start by rewriting cotangent as the cosine of x over sine of x. Then we have the natural log of sine of x dx. So you can see here that we're probably going to want to do some sort of U sub, and as we've talked about, 90% of the time, our best U choice is the function within another function. So we could try doing sine of x. So du is going to be cosine of x dx, which I see right here. So this will substitute out, and we could replace this and this with u, and then see how it looks. So it actually ends up being 1 over u times the natural log of u du. So from here, we could actually call this a double u problem. So I'll say a W problem where we need to do U substitution again. And I'll use a new variable, I'll use W. So for this one, hopefully you see that we have natural log of u and 1 over u. 1 over u is the derivative of natural log, so it's a perfect scenario to do U sub. So we could say W is natural log of u dw is 1 over u du. So we can substitute this out, we can substitute this, and we're just left with w. W dw, which we can integrate. It would just be 1/2 w squared plus c, and then we could substitute back in for w. So natural log of u squared plus c, and then we could substitute back in for u. So 1/2 times the natural log of sine of x, all of that squared, and then plus c. So again, you know, this is kind of a more advanced U sub problem because we have to do 2 rounds of it, but hopefully once you're able to kind of reduce it down, you notice, oh, I can do U sub again, and then it's much easier for us to integrate. Now, this problem is actually even more interesting because we can actually try a different U sub and get the same answer. Again, this might not be as intuitive, but let me rewrite the problem again over here. I'm still going to write it as cosine over sine. So for this one, if I actually set u equal to the natural log of sine of x, and I do that, and I take the derivative of that, we know that the derivative of cosine, this derivative is 1 over sine, and the derivative of sine we have to do, the chain rule here is cosine, and so we actually end up with exactly what we would like to substitute out. So we actually have a function and its derivative in there. So it actually works out really well. So it's the integral of u du, which of course would just be 1/2 u squared plus c, and then we could substitute back. So 1/2 times, and then our u value is natural log of sine of x squared plus c. So we end up with the same answer, so it seems a lot easier. However, I would venture to say that this is probably not a super obvious way to use U sub, but if you did notice this, of course, this seems much easier than having to do a W. All right, let's try another one together. So here, looking at this, if you tried U sub right off the bat, it's not quite going to work because of this sum within our numerator. So we can try the strategy of actually separating the numerator and actually creating, in this case, the sum of 2 separate integrals. So I'm going to rewrite it like this. The integral of x over the square root of 1 minus x squared dx plus the integral of 3 over the square root of 1 minus x squared dx. So hopefully when you've rewritten it like this, you see, oh look, this is definitely the structure for arc sine of x, which is 1 over the square root of 1 minus x squared. So this will be easy for us to integrate. We could just pull the 3 out front. And then for this one, we look at it, it doesn't quite fit this structure because of the numerator. So for this one, we will need to use u sub. So we can try u for 1 minus x squared, and du is negative 2x dx. So I'm going to move this out front. Okay, and then we have negative 1/2, and then we have 1 over the square root of u du. So this would give us 2 times the square root of u plus c. Zoom out. So we have negative square root of u plus c, and then we could substitute back in. So negative square root of 1 minus x squared. And then we could look at the other part here. Again, we can pull out that constant, and then it perfectly fits arc sine. So this will just be 3 arc sine of x plus c. So I'm just going to add this down here, plus 3 arc sine of x, and then we have our single plus c. So this is our final answer. So again, kind of knowing that you have this strategy in your pocket is really useful. It may not be super intuitive, but if you're looking at something and you notice you have a sum or difference in your fraction, U-sub just isn't working, try splitting it up. All right, so here's another example where we're going to use a new method that's maybe not super intuitive, but if you know that you have this as a potential strategy, it can be extremely useful. So if you have a rational function within your integrand where the degree of the numerator is greater than or equal to the degree of the denominator, a nice strategy to try is to use long division to rewrite and split up the fraction. So again, this is one where U-sub wouldn't quite work out so nicely, so let's give this other method a try. So we have x squared minus 4x plus 2 divided by x squared plus 2. It's 2, and then we're going to subtract, and then this gives us plus 0 here. So we could rewrite this as the integral of 1, and then we can say plus, and then we have our remainder over our divisor. So this is just a way to rewrite our original integrand in a form that might be a little bit nicer. So now we can use our sum property, and we can split up the two parts of our integrand. So 1 dx plus, or let's actually do, I'm going to pull out the negative and the 4. So x over x squared plus 2 dx. This we know is just a constant function, so it will just give us x plus c, but we'll add the c in later. And then for this one, we will have to do u-sub. So we can say that u is x squared plus 2 du equals 2x dx. So that allows us to rewrite this as minus 2 times the integral of 1 over u du, and then natural log of absolute value of u, and then here's our constant of integration. And then we could just substitute back in. So 2 times the natural log. We know that x squared plus 2 is always positive, and then we have plus c. So again, by splitting up our fraction by doing some long division first, we have something that's much easier to work with than our original integrand. All right, let's try another one together. So for this one, you wouldn't be able to use u-sub right off the bat for this one, but we can try, again, that method of dividing because the numerator degree is larger than the denominator. So we can do x cubed divided by x squared plus 1. And then we subtract, and we're just left with negative x. So this integrand we can rewrite as x plus negative x over x squared plus 1 dx. So then we can split that up. And then I'm going to pull out the negative. And then we can see, well, this we can find the antiderivative for pretty easily, x squared. And then for this one, we can use u sub. So we have minus 1/2 and then 1 over u du. I'll add in my constant of integration after. So value of u plus c. And then we'll substitute back in for u. This function is always positive, so I no longer need my absolute value signs. Plus c. And if you want, we could use our power property of logarithms and move this exponent up front, or up top here. So it's the power of 1/2, so it's a square root. So we can actually say minus the natural log of the square root of x squared plus 1 and then plus c. Although they're completely equivalent, so either way I think is totally fine. So again, just knowing that if the degree of your numerator is greater than or equal to the degree of your denominator and u sub's not working out, try rewriting using long division. All right, here's one for you to try on your own, so please pause the video and give it a shot. All right, go ahead and take a look here. So I did my long division to rewrite it as 4 plus negative 4 over x squared plus 1. So I split it up into two integrals. And when I pulled out the negative 4, I could see that I have the exact structure that works for arctangent. So it's a pretty nice problem after you rewrite it. All right, so looking at this next problem, we're going to try it together. U sub won't really work. We can't. We won't want to use long division. We can't split up the numerator. So we're going to try completing the square within our polynomial so we have a binomial squared. Just so you can kind of picture, why would we want to do this? Well, because a lot of our derivative rules have x squared. If we have arctangent, it's 1 over 1 plus x squared. For arcsine, it's 1 over square root of 1 minus x squared. So perhaps if we can create this squared term, we can use u sub and use one of these rules. And it's typically going to be for an inverse trig function. So let's try completing the square in our denominator. So if I'm just looking at the first two terms here, we have x squared plus 4x. The number that completes our square is 4. But we need to make sure we're maintaining the same value as our original expression. So originally it said plus 8, so then I'm going to add another 4, so it's still plus 8, but I'm going to keep them separate, so then I can rewrite this as x plus 2 squared plus 4. So from here I can see that maybe I'm getting closer to this structure for arctangent. But it would be much nicer if this were 1. So maybe I'm going to factor out a 4. So when I do that, so I have 1/4, I'm factoring out just from my denominator. That leaves us with 1 over x plus 2 squared over 4 plus 1 dx. And then I see I can pull this 1/4 out front, and then I can add this into the term that's being squared. So I can say that it's x plus 2 over 2 squared plus 1 dx. So now I see that I've created this structure, the structure for arctangent, but I will just need to do some u sub so it fits the structure exactly. So I'm going to say u equals 1/2 x plus 1. That's the inside here. So we have du equals 1/2 dx, so 2 du equals dx. So when I do my u sub, my 1/4 gets multiplied by 2. So I have 1 over 1 plus u squared du. So then I see, okay, this now fits the exact structure for arctangent. And then I just need to substitute back for u. So 1/2 arctangent of x plus 2 over 2 plus c. And there you go. So again, we're really going out of our way to create this structure that we're more comfortable working with. Again, not super intuitive, but that's the whole reasoning behind why would we ever want to create to complete the square, because a lot of our rules have that term being squared. All right, let's try one last one together. So here you can see we don't really have any other options but to try this completing the square. So within our square root, we're going to complete the square. So I'm going to do a little bit of rewriting first. So I'm just going to rewrite it in this order. So negative x squared minus 6x plus 7 dx. So here we can't complete the square if the a value is not positive 1. So we're always going to factor out that negative. So then we have x squared plus 6x. Now the number that completes that square is plus 9. But really what we did was we actually subtracted 9. So I have to add 9 to balance it, and then we still have that plus 7 that we had from before. So this just makes sure that we have the same overall value that we started with. So I can rewrite this now like this. The square root of negative x plus 3 squared plus 16. So hopefully we can see that we're kind of moving towards this structure, which would be for arc sine. But we would like to have a 1 here, so we're going to need to do a little work to take care of this 16. So let's imagine I factor the 16 out. And if I do that from within, that 16 turns into a 4 out front. And then on the inside, I would have 1 minus x plus 3 squared over 16 dx. And I forgot my dx up here. And then from here, I can pull this 16 into this term being squared. I can also pull my 1/4 out front. And I have the square root of 1 minus x plus 3 over 4 squared. And now I do have that structure for arc sine. I still need to do some u sub, so I can u sub for x plus 3 over 4. So du is 1/4 dx, so 4 du equals dx. So when I substitute, the 4 multiplies to the 1/4, and it actually just turns to 1. So I have 1 over square root of 1 minus u squared du, which actually fits perfectly for our structure for arc sine. So we have the arc sine of u plus c, and then we just substitute back for u. So we have the arc sine of x plus 3 over 4 plus c. So there you go. So again, I wouldn't necessarily say this is an intuitive strategy to use or something that's like super easy right off the bat, but if you've kind of seen enough of these problems, you start to notice patterns and how you can manipulate your integrand to look like one of the structures that we like to work with. All right, I have one last problem for you to try on your own, so please pause the video and give it a shot. All right, go ahead and take a look here. So this problem I'd say is definitely a challenge problem, and you actually need to use a couple of the strategies we talked about today. So first we can complete the square, which gives us an expression that looks like this. Now, I know this looks very close to the structure for arctan, but for this one we have that variable up top. So we can try using u sub. And to get rid of this x, when we set u equal to x plus 3, we can say that x is equal to u minus 3. So that allows us to eliminate all of our x's, and we have this. Now from here, the strategy we can use, another one we talked about today, is splitting up the numerator. So when I do that, what I end up on the right, I pull the 3 out front with this 3, so that's how it's -9. But this is the exact structure for arctangent, so that's kind of nice. And then for this other side, we've done a few other problems very similar to this today. From here, we can do another U sub, but I'll use W for a different variable. And so then we end up with something we can integrate with. And then as we go to substitute, first we substitute back in for W, and then we have to substitute back in for U, which was our original substitution of x plus 3. So I know it looks kind of like a scary problem, but it does utilize a couple of the strategies that we use today, which is nice. So remember completing the square, breaking up fractions, trying long division to rewrite a fraction. Those are all great strategies to try when U sub doesn't initially work. All right, that is all for today's video. Thank you so much for watching.